Welcome to magnification and calibration. In this video we're going to be essentially learning how to use a microscope and how to make sure it is accurate, because that's what calibration is. We're making sure that something that we're using is accurate. Here is the summary slide. All of this is available at my website completely for free, which I'll put the link in the description at stemcelltuition.com/free workbook, and you can download all the resources completely for free. What we're doing in this video is we're working out how to calibrate a microscope. Well, what does that mean? That means that we are making sure that the microscope is as accurate as possible. And to do that, we're going to use two things. So there are two lenses that we use on a microscope, the eyepiece lens and the objective lens. When we look down the eyepiece lens, we're going to see some kind of scale, also known as a graticule. Now, there is no unit, or sometimes given as arbitrary units, which essentially means that there isn't an actual number here and it can change. And what we're going to do is we're going to take this thing here called a stage micrometer. Now, they come in all different variations, and you might get some clear ones, you might get some black ones. A really common one that you get in school is where you have like an A and a B section. And what a stage micrometer is it's made in an industry, and we can assume that it's highly accurate. And we're going to take this highly accurate scale that's tiny, microscopic, and we're going to align it with this inaccurate scale, and we're going to give a value to these numbers. And we're going to create a ratio of the amount of this scale which matches up with that one. Now, this can be quite hard to get your head around, so just a couple of key principles. So the stage micrometer or micrometer is the accurate one, and all we are doing is we're matching that to the eyepiece graticule, and often the unit that we make after that is known as an ocular unit or an eyepiece graticule unit. So the first step is put the stage micrometer onto the stage. Once you've got there and you look down the microscope, you're going to see something like this. Now, I've superimposed down here, this is my stage micrometer, this is my highly accurate one, and then this one here, this is kind of what it looks like as you look down the eyepiece, down the microscope. I've tried to recreate situations that will match the PAG. If you're an OCR A student, one of the skills that you have to do is you have to calibrate a microscope. And what we're saying is that the numbers on the scale, so let's say the start, and this is the one we're starting on, at times 4 objective lens and times 10 eyepiece lens, which gives us a total magnification of times 40. You times them together. At this magnification, it might not be quite times 40. So we need to work out what the actual length of this is. So step 1, you can line any two places, it doesn't really matter, but it just makes it easier to begin with if you line up the two zeros next to each other, and then you match up this micrometer with the eyepiece graticule. Now, most micrometers are going to be 1 millimeter, which is equivalent to 1,000 micrometers. Now, it will say that somewhere on the stage micrometer, often very small, but visible with the naked eye. It will say what that length is. And then we can create a ratio. We can know what the stage micrometer is, and we can create a ratio with the eyepiece graticule. So in this case, the eyepiece graticule, and let's just say these numbers match perfectly to start with, the eyepiece graticule is 4, and the stage micrometer, now these numbers are 100, normally it's 1,000, so this is 100 divisions of 1,000 micrometers, so that's equivalent to 1,000, and then treat it like a ratio. So we want to find out what 1 micrometer is. So if I divide any number by itself, you'll get 1, so 4 over 4 is 1, and whatever you do from one side of the ratio, you do the same to the other. Therefore, 1 is now equivalent to 250 micrometers. So now we can remove the stage micrometer, we can put some kind of cell that we want to observe on the stage now. So we take off the stage micrometer, we put on a slide that we want to observe, and now we can measure it. And we now know that the length of one large division, and you can divide it by 10 to get the small divisions, is 250 micrometers. I can measure the whole length of whatever the specimen is. So let's say this goes from 7 to 1. So that's 6. So I can do 6 times 250, and that tells me the length of whatever this cell is, 1,500 micrometers. Now, that's if things work perfectly. More often than not, it doesn't quite match up. So this is where you get decimal numbers. So what we're going to do now is we're going to say that this reads up here to 4.1. And this is what's likely to happen. The lens, when you look down it, is unlikely to be, as we stated at the beginning, exactly right. It could be somewhere between sort of times 40 and times 39. So we want to know what the true length of this measurement is. So we do the same process again. So the eyepiece graticule this time is 4.1. The stage micrometer, it's still the whole stage micrometer, so it's still 1,000 micrometers. So I can put the micrometers in the heading here. Okay, and there's no units for the eyepiece graticule. This time I'm going to divide both sides by 4.1, and that gives me a reading of roughly 244. So I've just rounded it from 243.9 upwards. So now, actually, we're out by 1 micrometer, and that is the importance here. If we're working in a biomedical lab and we're observing tiny, tiny bacteria, we need to make sure that we're measuring the bacteria the correct length of them, because that's going to help work out what bacteria that is and maybe diagnose a patient. So this was at ×40 lens, and now when we increase the magnification, so when we rotate the objective lens now, and we're now going to put in the objective lens ×10, well, I've got ×10 in the eyepiece all of the time, so now we're going to go up to ×100. Now on ×100, you'll see that the exact same stage micrometer will have zoomed into it. You've increased the magnification. Now, the standard thing that you're going to see for A-level biology in your OCR A is that ×100 magnification, it should roughly be about equivalent to 1,000 micrometers. So we do the same process again. So I'll demonstrate it one more time here. So the stage micrometer, the full length of it, I'm just going to pretend those zeros line up. I'm going to pretend they line up perfectly, and then we'll do it accurately afterwards. So the stage micrometer is 1,000, and the eyepiece graticule is 10. Any number divided by itself is 1. So 1 is equivalent now to 100. So I'm saying now the exact same eyepiece graticule hasn't changed. Previously it was 250. Now the same eyepiece graticule is now equivalent to 1,000. But as we can see, this doesn't match up perfectly. So we can start again. And we're now going to try and do it a little bit more accurately. And in reality, you would put them on top of each other. I've just done it here so you can see them. So let's say that is equivalent now to 0.1. And let's say this one matches up here now to 9.9. So the difference between the two is 9.8. So we start again. So this time, the eyepiece graticule is 9.8. And the stage micrometer is the whole thing. So the stage micrometer is 1,000. So I'm now going to divide both sides by 9.8. This time round, it's roughly giving me 102. So now that I'm saying that one full division is equivalent to 102 micrometers. Previously, it was about 250. And now we're going to look at the ×40 objective lens, which at school is normally the most powerful one. The eyepiece is 10, so again, we're at ×400. And as you can see now, I've really had to magnify the stage micrometer. And you'll see this. So the lines themselves will look thicker as you look down the microscope. The eyepiece graticule stays the same. And now you'll find that it's about 1/4 will only fit. So if I'm observing down the eyepiece, essentially what's happening is, so now the stage micrometer is completely out of view. So you won't see it all. So you just have to take a section of it and read from that section, but you follow the same process. So this time round, the stage micrometer, I can only see from 0 to, let's use this 2.5 up to 10 there. So or 20.5 to 25, that would be equivalent to 250 micrometers. So I can't get the whole stage micrometer in, but that doesn't matter. And that's equivalent from 10, but the 0 this time is going to match up, let's say that's from 0.5. So that the eyepiece graticule now is 10 minus 0.5 is 9.5, and we do the same process again. We divide both sides by the eyepiece graticule, and that gives us a ratio of 26:1. So now we're saying that the width is 26. Now the original one was about 250. We've gone from 40 magnification times by 10 to 400 magnification. We start on the ×4 lens. We're now on the ×40 lens over here. So we've increased from 250 to 26, which is roughly ×10. Now this little table here is what you can use for your PAGs to organize what you're doing. So this is an example here. So here's my objective lens, here's my stage micrometer, these are the number of eyepiece graticule units, so this suggests that it really is not right, that the accuracy of the microscope is really far out. So previously, the example I gave, that was equivalent to 100, so it's really significantly out, nearly 20% out this lens. Now just to give you some general ideas, so if you're starting your PAGs on this, regardless of which one you do, in the 1.1, 1.2, 1.3, and if your school makes any, they can make extra themselves, these are the rough numbers that you're going to see. So at the ×4 lens, you're going to roughly see that the width of, if it goes up to 10, so 1/10 of whatever the division is normally, is going to be equivalent to 250 micrometers. So one division, or 1/10 of the total, is normally equivalent to 250. at times 10 objective lens, it normally works out as about 100 micrometers, and at times 40, it's normally about 25. So if you haven't got a number that's close to 250, 125, you've probably gone wrong somewhere. Now you don't have to line the zeros up. You could put the micrometer in there and it would work the same way. You would just be doing the change in the eyepiece graticule rather than from 0 upwards. Now this can be applied in an exam question in a variety of ways. So you can pause the video and have a go at this one. So the top scale is the eyepiece graticule and the bottom scale here is the stage micrometer. And they're saying one division from there to there is 10 micrometers. They're saying that a xylem vessel has a diameter of 21 units on the eyepiece graticule scale. So it's 21. So we'll just double check there's 10 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So we're saying up to there. So we're saying that what we're observing, which is a xylem vessel, has 21 units on the eyepiece graticule. But that's arbitrary units. There is no unit there. So now we have to do the conversion over. So 21 is equivalent to 7 on the stage micrometer, but each division on the stage micrometer is 10, so that's equivalent to 70, so the answer is C. And here's a really tricky one. In this question, what they've done is they've essentially done the calibration for you. And what they have observed is 20 micrometers is equivalent to 2.35 divisions on the graticule. So pause the video and see if you can have a go at this one without my help. Okay, so the very first thing that we need to do is we need to work out what one division of the graticule is. So we can use the same table that we did previously. So the stage micrometer equivalent is 20 micrometers. So in the units of micrometers. The eyepiece graticule is equivalent to 2.35. So if we divide both sides by 2.35, that will give us a score of 8.51. I'm going to stay to 2 decimal places because they have used 2 decimal places in the question. And as a general rule for A-level biology, follow the number of decimal places and significant figures in the question. If they don't explicitly answer it, just follow. The reason why they get you to do that is because if you add extra decimal places in, you're suggesting that the graticule has a higher level of accuracy, which it doesn't. So now the question itself is asking us about the nucleus of cell C. It would be really easy to not spot the word nucleus. It's just the nucleus. Now what you want to do here is not draw lines down, because that's going to leave inaccuracies if you do it at a funny angle. You want to physically measure the width of that and then lay that width on top of the graticule. Let's say it comes out to 1.4 on the graticule. Remember, this is starting at 1, not at 0. So from here to here where my red line is, that's 1.4. So now all you do is you do 8.51 times by 1.4, and that would give us the length in micrometers, which I've got as 11.91 micrometers. Whenever you do any question here, I'm going to check for units. It hasn't made it really clear which units we have to use, but there's micrometers in the question. It wouldn't make any sense to convert this to millimeters now. Now with a question like this, they'll normally give you quite a little bit of leeway in terms of the measurement because it doesn't perfectly go on. So they actually, in this question, so the answer was 11.91, but they actually gave you a little bit of leeway of 1 division on the graticule either side. This is magnified on my screen, but on the exam paper it would have been smaller than this. So they've allowed essentially 1 millimeter either side. So you could still get full marks as long as you've followed the conversion the same and then multiplied it by your division the same. I hope that was helpful. You can go into my next video where we're going to be looking at types of microscopes, which is transmission and scanning electron microscope, along with the classic light microscope we used today. See you there.